How you doing, everybody? Today we're going to continue talking about circuits, and we're going to do this a little different. I'm going to try and make this as fast as I can, but today we're going to go through the two types of circuits. Well, there are really three, but one of them is a combination. But we're going to go through two types of circuits. I'm going to introduce the mathematical circuit rules, but we're not really going to solve any of them today. And then I'm going to go through just drawing one or two examples. So as you can see, here are my circuit diagrams, and this is one type of circuit. One type of circuit is a series circuit. Now, if you ignore these suckers for a second, just look at this little simple circuit. A simple circuit is just a circuit that is connected. Again, this thing is the battery. We got those symbols last time. The battery connects to what this is, a resistor, and then connects to the other side of the battery. It's a circuit with one thing in it. It doesn't matter what this thing is. It's a circuit with one thing. It could be a resistor, a light bulb, a transistor, a diode, anything we have, but just one thing. Now, these other guys that are in series, they technically look the same because by definition, a series circuit is a circuit that has exactly one path for electricity to get through. So that means the wires are connected to one side of the battery or the power source, to the other side of the battery or power source. And then anything that happens in there, all of the electricity has to go through it. So these two resistors would be said to be hooked up in series. The electricity goes through resistor 1, through resistor 2, to the negative terminal. Remember, this is a potential difference. High potential on the top, low potential on the bottom. This is a series circuit with 3 resistors in it. And again, doesn't matter what we're putting in there. These pictures are just with resistors. We can go 4, 5, 6 resistors, a resistor, and a light bulb. It doesn't really matter. Now, this diagram, these two diagrams are parallel circuits. What a parallel circuit means is there are 2 or more paths for electricity to go through. Now notice that these two things are parallel. That's not exactly what we're looking for, because if I go back, if I pretend this isn't here, this resistor is in parallel with that resistor. In other words, they're parallel lines, but it's still a series circuit. Only one path for electricity. These two are in parallel, and there are multiple paths. So that means electricity comes, when it gets to this is called a junction. It gets to that junction, it can go down through this resistor, then back to the battery, or it can be going this way, electricity is traveling. It doesn't go through this junction. It goes through this junction and through the resistor all the way back to the battery. The same thing happens here. We have path number 1, we have path number 2, or path number 3. And they all connect to the top and bottom. Now, what you may be able to visualize already, one of the differences is these are like the old cheap Christmas lights maybe you have, or I should say holiday lights maybe you have at home. In other words, if this resistor breaks, electricity gets stuck here. There's nothing going through this one or this one. So we say in a series circuit, if one light goes out, the whole circuit goes out. All lights go out. So if any resistor, even if it's this middle one, electricity would go through here, but then if this one's broken, it gets stuck. So then that's out, that's out, that's out, because we need to connect the top and the bottom of the battery all the time. Here in a parallel circuit, if this branch doesn't work, it doesn't matter, because electricity, you're like, it doesn't work there. So it just keeps going, goes through this one, and then touches the bottom of the battery. Multiple paths, the same thing. If this one doesn't work, I would have electricity going through path number 1. Whoops. And going through path number 3. So that is one of the differences between series and parallel. Now, one thing we haven't talked about are meters. Now, meters do exactly what you'd expect. They measure things, like a speedometer measures speed. A voltmeter measures the voltage or the potential difference across two things. Remember, potential difference means I need to measure in 2 different spots. So if I wanted to measure the potential difference, say, across that resistor, I would need to measure it before the resistor and after the resistor. Same thing on a series circuit. If I wanted the potential difference of this resistor, I need to measure before and after. And we'll see that when I draw them. An ammeter measures the current, or all of the electricity going through. Meaning an ammeter pretty much sits there and counts electrons as it goes. So it can just be placed in one spot in series. So if I look at any one of these, if if I put an ammeter right there, so this little guy like Mr. Joyce size, right there, and it would just be counting 1, 2, 3, 4, 5, 6, 7, all those electrons, because we know current is the number of electrons per second, so we could just count, or an ammeter literally just counts or measures how much electricity is flowing past. So that's a difference in my meters. Again, you'll see how I draw them when we put them into the circuit. Now, this is an example of a closed circuit. Now, again, what I like to do when I have a switch, because there's no switch here, and maybe I needed one, what I forget, I would just put 2 dots there. See this little dot there? And then I put a little dot here, and then I put a straight line through. That would recommend, or that would be like a closed switch. Most of the time, we don't do that. So this picture, and the reason why I chose these 3 pictures, are because they show all very similar things. A resistor with a circle around it, that is acceptable for a light bulb. That's not what we saw last time. Most light bulbs are this little curly Q, also with a circle. That's also a light bulb, or sometimes called a lamp. Every once in a while, this is antiquated. There's an X with a circle on it. That also means a light bulb, but we rarely see that. Now, the other thing that's important in this is this word conventional current. We already talked about that. Conventional current is just our convention. It means electricity comes from the plus. If this switch was closed, close that switch, electricity can flow, and we define it in that direction. In a higher level class, like a college class, they might talk about electron current. That's just the opposite. We do not talk about electron currents in our class. I just want you to be aware that it exists. The direction really doesn't matter. We define that. So we define it going from high potential, from the top of the battery, all the way to the bottom of the battery. I'm going to skip that guy. No, I'm not. I'm lying. The voltage drop. Now, voltage drop is the same thing as the voltage difference, the potential difference across thing. Now, we're going to talk about series circuit first. I want to do this in 3 minutes or less. The series circuits, all of the voltage needs to add up. In other words, the voltage is the push, right? It's pushing the electricity. So if I have multiple things I need to push through, if I have all of my energy and I use it all, if I put 2 of you standing right next to each other, if I use all of my energy to push this person, I have nothing left. That person can just laugh at me. Ha! But if I use some here and some here, I can push that guy and push that guy. That's what voltage does. So our voltage here, if I say voltage 1, or the potential difference from that resistor and that resistor, notice how they're different? That means the resistances are different, but the battery must be a 9-volt battery, because 4 plus 5 equals 9. So my rule is the total voltage is voltage 1 plus voltage 2. If there was another one, another resistor, there would be voltage 3, another resistor, there would be voltage 4, etc. That is my voltage rule, or my potential difference rule. My current rule is different. Now, in a series circuit, this one's the easiest one. Current always stays the same. Why? Because the current goes through the entire circuit. It's the actual electricity. So all of the electricity here goes through this, goes through this, goes through this wire. The current in a series circuit never changes. You ready for this equation? The total current is the same everywhere. It's nice and easy. Last is the resistance rule. Now, this is something that's called an equivalent resistance, and this one makes sense too. Parallel circuits are a little harder. In a series circuit, we're going to talk about that push again. If I have to push through this resistance, electrical friction, and through this resistance, electrical friction, it's going to be harder. The more stuff I have to go through, the harder it is. So my resistance, the equivalent resistance, I bet you can guess, would be good, 30, because 10 plus 20 is 30. So the equivalent resistance, or the total resistance of this whole circuit, is 30 ohms. Here's my equation. Resistance, R1 plus R2, if there was a third one, plus R3. This little Rn means just however many there are, we add them all up. So those are my series rules. In parallel, they're a little different. Parallel, the voltage is the same everywhere. Well, why is that? Because remember, the voltage is the push. And when the electricity gets to this junction, I have an option. Remember, if I'm talking about this push, I could literally go push down on this one and totally ignore that resistor. Or I could come up, ignore that guy, and push my way through that one. So in a parallel circuit, the voltage at each branch is the same. So the total voltage here is the same as the total voltage in this branch is the same as my power source. It's opposite of what we saw for series. Series, the current was always the same. In a parallel circuit, the voltage through every branch is always the same. Well, that also must mean maybe my current is different. Now, what do you think here? Remember, current is the actual electricity. So I've got electricity going, gets to this junction. Some gets to go this way, some gets to go that way, which means the total must be 4. 1 plus 3, which means the total current is all the current through one branch, plus all the current through a second branch, plus all the current through a third branch. Looks like that. I1 plus I2 plus I3, etc. Now the resistance rule, and the total is 4. We already saw that. The resistance rule is very tricky, and I'll explain this one in the future. But essentially, if I have parallel resistors, you can think about it as standing on line, or if you're at a toll booth. If in series, everyone's going through the same one, it takes a lot longer, right? But in parallel, if I have multiple ways that my electricity can go, like multiple tellers at Marshalls, or, Marshalls, you have that big zigzag, everyone's on line, but then at the end, there are multiple tellers, so it goes faster. Resistance in parallel goes down. So the total resistance goes down. What you want to remember, a series circuit, the more resistors, the higher the resistance. In parallel, the more resistors, the lower the resistance. And it's going to be lower than the smallest one. So my equivalent resistance is going to be something less than 10 here. The way I calculate it is hard. 1 over the equivalent resistance, 1 over R1, so 1 over 10, plus 1 over 20, plus 1 over however many other resistors there are. We will practice that math. It gets a little tricky. In this case, we'd have 1 over 10 plus 1 over 20. Well, I would need a common denominator, which is 20. So 2 over 20 plus 1 over 20 is 3 over 20. And then I need to take the reciprocal. So my equivalent resistance is 6.67 ohms. We will practice that, don't worry. Just to compare all of my rules, unfortunately, you need to memorize these. And we'll practice them, and I'll give you different ways to memorize them. This is something that is never given to you. Now, when I say you have to memorize them, obviously you're at home. I'm talking about if there's an actual MCAS this year, these are not given. We need to know these equations. Anyway, that's all I have for you on this. I'm going to just draw 2 examples, so it'll be a little bit longer. You stay put while I set this up. You're not even going to know I set it up. It's going to be a pause.